Max Planck, born in 1858 inches, Kiel, Germany, would go on to become one of the most pivotal figures in the history of physics. His journey into the world of science was not one of immediate fame or grand recognition, but rather it was a slow and steady ascent, marked by his deep curiosity and a relentless drive to understand the fundamental laws of nature. Raised in an environment steeped in academic tradition, Planck's early education was shaped by a strong intellectual atmosphere. His family was academic, with his father being a professor of law, and this environment naturally influenced young Max's interest in learning. At an early age, he exhibited an extraordinary aptitude for mathematics and physics, disciplines that were to become the cornerstone of his later groundbreaking work. Max Planck's formal education began at the University of Munich, where he initially studied engineering but quickly turned to physics, a decision that would steer the course of his life. Planck was introduced to the world of theoretical physics under the guidance of prominent professors. His academic journey took him to the University of Berlin, where he studied under renowned physicists of the time, including Hermann von Helmholtz. It was here that Planck's interest in thermodynamics and the laws governing heat and energy began to take shape. However, it was in the latter part of the 19th century that Planck found himself at the crossroads of a major scientific challenge that would define his legacy: the problem of blackbody radiation. The turn of the century was a time of significant scientific upheaval. Classical physics, which had been developed over centuries, seemed to have reached its peak, with theories of motion, energy, and matter thoroughly explained by the works of Newton and others. Yet, a paradox had emerged that could not be reconciled by existing theory: the blackbody radiation problem. Blackbody radiation refers to the electromagnetic radiation emitted by a perfect black body, an object that absorbs all light and reflects none. The nature of this radiation puzzled physicists, as classical thermodynamics and electromagnetism failed to accurately predict the observed radiation emitted by black bodies at higher temperatures. Classical theories predicted that a black body should emit infinite energy at shorter wavelengths, particularly in the ultraviolet region, a scenario that was clearly impossible and led to what was known as the ultraviolet catastrophe. Theoretical work by Wilhelm Wien and others had already tried to describe blackbody radiation but fell short in accounting for the behavior at high temperatures. The classical laws simply didn't work, and the field was at an impasse. It was against this backdrop that Max Planck, then a relatively unknown physicist, entered the scene. Planck's approach to solving the black-body radiation problem began in 1899, when he became increasingly interested in understanding how radiation behaved at various temperatures. He realized that the existing theories were insufficient, as they did not take into account the possibility that energy might not be distributed continuously, as was assumed in classical physics. In a bold move, Planck suggested that energy could be quantized, that is, it could be emitted in discrete packets, or quanta. This hypothesis was revolutionary because it broke from the classical assumption that energy was continuous. Planck's proposal was a mathematical leap based on the empirical data of black-body radiation. In 1900, after much mathematical work, Planck introduced his now famous formula, which fit the experimental data perfectly and solved the ultraviolet catastrophe. The formula demonstrated that the energy emitted by a black body was not continuous, but rather was quantized in discrete units proportional to the frequency of the radiation. Planck's idea that energy was quantized was groundbreaking, but he himself did not immediately appreciate the full significance of his discovery. In fact, he initially believed that his quantum hypothesis was merely a mathematical trick, a temporary fix to address the radiation problem. Planck had no intention of challenging the classical view of physics or introducing a new paradigm. He viewed his work as a provisional solution that would be later supplanted by a more comprehensive theory. However, as the years went on, Planck's quantum hypothesis proved to be far more revolutionary than he had anticipated. It was the first step in a long line of discoveries that would fundamentally alter our understanding of the physical world. It is important to note that while Planck introduced the idea of quantization, it was Albert Einstein's later work on the photoelectric effect that showed the true power and importance of quantum theory. In 1905, Einstein used Planck's quantization of energy to explain the photoelectric effect, which further demonstrated the existence of discrete energy levels in light. This work earned Einstein the Nobel Prize in Physics in 1921 and solidified the legitimacy of quantum theory. Despite this, Planck remained somewhat skeptical about the radical implications of his own ideas. He continued to see them as a mathematical tool rather than a profound shift in the understanding of the universe. In many ways, Max Planck's contribution to science was like the spark that ignited the flame of quantum mechanics. His work laid the foundation for a new paradigm in physics, one that was initially met with resistance but would ultimately change the course of scientific history. His quantum hypothesis challenged centuries of established thought and opened the door to a completely new way of thinking about the universe. Yet, Planck's theory alone was not enough to build the full structure of quantum mechanics. It was his successors, such as Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, who would take Planck's initial insights and expand upon them, creating the rich and complex framework that we now know as quantum mechanics. Max Planck's contribution did not end with the formulation of his quantum hypothesis. Over the years, he continued to contribute to various fields of physics, including the development of the second law of thermodynamics and the understanding of entropy. His work in thermodynamics was closely tied to his interest in energy, and he sought to understand the flow and distribution of energy in different systems. Planck's research into the laws of thermodynamics reinforced his belief in the fundamental nature of energy and its relationship to the fabric of the universe. However, it was his work in quantum theory that truly set him apart as one of the greatest scientists of all time. Despite the revolutionary nature of his work, Max Planck's life was marked by personal tragedy and a sense of modesty. His career spanned both world wars, and during the Second World War, he lost both of his sons. Throughout these difficult years, Planck continued to work, driven by his passion for science and his unwavering commitment to the pursuit of knowledge. He was not a man of flamboyance or grandiosity, but rather a quiet and determined individual who saw science as a means of understanding the fundamental truths of existence. Planck's work was not only significant in its own right, but also served as the catalyst for a scientific revolution that transformed our understanding of the universe. Quantum mechanics, the theory that emerged from his early insights, is now one of the pillars of modern physics. From the strange behavior of subatomic particles to the development of technologies like semiconductors and lasers, quantum mechanics has had a profound impact on every aspect of our lives. It has changed the way we understand everything, from the fundamental structure of matter to the workings of the cosmos. As we reflect on the life and work of Max Planck, we are reminded of the power of curiosity and the importance of questioning established knowledge. Planck's willingness to challenge the assumptions of his time, despite the prevailing scientific orthodoxy, paved the way for one of the most transformative revolutions in science. His work has inspired generations of scientists, and his legacy continues to shape our understanding of the physical world. Max Planck's contributions to science did not just end with his work on black-body radiation and the formulation of quantum theory. As his discoveries gained wider recognition, they became the cornerstone upon which the whole of quantum mechanics was built. Planck's work had profound implications, not only for the scientific community of his time, but for the generations that followed. His legacy transcends the specifics of his theories, embodying a shift in how science, and indeed our understanding of the universe, would unfold. The principles he established would ultimately lead to the development of quantum mechanics, a theory that would go on to explain some of the most fundamental phenomena in physics. Following Planck's discovery of quantized energy levels, a ripple effect was created throughout the world of physics. He introduced the idea that energy could only be emitted or absorbed in discrete quantities, known as quanta. This concept was novel, as it ran counter to classical physics, which had posited that energy flowed continuously. However, Planck did not fully embrace the implications of his own work. His reluctance to fully acknowledge the revolutionary nature of his discovery led to a somewhat hesitant approach towards what would later become the quantum revolution. His work was seen as a stopgap measure rather than a complete overhaul of the classical paradigm. Yet, despite his own reservations, Planck's ideas provided a pathway for others to build upon. In the following decades, his quantum hypothesis sparked the imagination of other brilliant minds. Albert Einstein, in particular, found great utility in Planck's work when attempting to explain the photoelectric effect in 1905. Einstein's explanation showed that light was not only a wave, but also exhibited particle-like properties, giving rise to the concept of the photon. This was a direct consequence of Planck's quantization of energy. Einstein's work on the photoelectric effect earned him the Nobel Prize in Physics in 1921, and it solidified the credibility of quantum theory. At the same time, Niels Bohr was working on his own interpretation of atomic structure, which also relied heavily on Planck's quantum hypothesis. Bohr's model of the atom, proposed in 1913, was a critical advancement that incorporated the idea of quantized energy levels in electrons. Bohr suggested that electrons orbit the nucleus in discrete energy levels, and they could only jump from one energy level to another by absorbing or emitting a quantum of energy. This model explained many of the mysterious features of atomic spectra and was a direct extension of Planck's quantum theory. As quantum mechanics evolved, it became clear that Planck's discovery was not just an isolated breakthrough, but rather a foundational element in the understanding of subatomic phenomena. In the 1920 seconds, the development of quantum mechanics as a fully fledged theory took shape through the contributions of Werner Heisenberg, Erwin Schrödinger, and Paul Dirac. Heisenberg's uncertainty principle, which posited that one cannot simultaneously know both the position and momentum of a particle with arbitrary precision, built upon the quantum theory that Planck had initiated. Schrödinger's wave mechanics, on the other hand, gave a mathematical description of how quantum particles behaved as both particles and waves, adding yet another layer to the expanding quantum framework. The development of quantum mechanics marked the beginning of a new era in physics, one that challenged and ultimately superseded the classical physics established by Isaac Newton. Quantum mechanics provided explanations for phenomena that classical theories could not, such as the behavior of electrons in atoms, the properties of semiconductors, and the functioning of lasers. These advancements had a direct impact on technology, giving rise to innovations that shape the modern world today, such as computers, smartphones, and medical devices like MRIs. Without Planck's initial insight into quantization, these technologies might not have been possible. Despite the monumental nature of his discoveries, Max Planck remained a modest and somewhat reserved figure throughout his career. His dedication to science and his unassuming demeanor made him a figure of great respect within the academic community, but he did not seek fame or recognition. In fact, his life was marked by personal hardships that included the loss of his sons during the turbulent years of World War II. Despite the personal tragedy, Planck continued his work undeterred, maintaining a sense of duty to the pursuit of knowledge and the advancement of science. Although he was often at odds with the philosophical implications of quantum theory, particularly its departure from classical determinism, Planck's scientific integrity remained unwavering. He was never fully comfortable with the implications of quantum mechanics, particularly the idea of uncertainty and probabilistic behavior at the subatomic level. Nonetheless, his work in quantum theory paved the way for others to further develop the field and refine its conceptual framework. Max Planck's influence on modern physics cannot be overstated. He provided the initial spark that ignited the quantum revolution, and his ideas have had lasting impacts on both the theoretical and practical aspects of physics. As the 20th century progressed, quantum mechanics became one of the most successful theories in the history of science, and its applications permeated every facet of modern life. The advent of quantum theory also introduced new paradigms in philosophy, forcing scientists and philosophers alike to reconsider the nature of reality itself. The wave-particle duality of light, the uncertainty principle, and the concept of superposition have all reshaped our understanding of the universe at its most fundamental level. Planck's most enduring legacy lies in the fact that he was the one who lit the first flame of quantum theory, offering a glimpse into a new world where energy and matter did not behave as classical physics predicted. His discovery, initially a mathematical curiosity, grew into a theory that would redefine physics in the 20th century and beyond. It has influenced fields as diverse as quantum computing, nuclear physics, and even cosmology. The impact of his work continues to resonate in ongoing research, and his contributions remain foundational to the scientific enterprise. In addition to his theoretical work, Planck's approach to scientific inquiry and his commitment to intellectual honesty set a model for future generations of scientists. Despite the upheaval and tumult of the two world wars, Planck's resilience in the face of personal and professional challenges speaks to the tenacity and dedication required for scientific progress. Planck's contributions not only changed physics, but also exemplified the importance of perseverance and intellectual curiosity in the quest to understand the natural world. Max Planck's story is one of intellectual courage and vision. His groundbreaking work on blackbody radiation and the quantum hypothesis was a catalyst for the most significant revolution in physics since the time of Newton. His scientific achievements reshaped the course of physics, and his legacy continues to inspire scientists to question the boundaries of knowledge. Today, Max Planck is remembered not only for his pioneering contributions to quantum theory, but also for his deep commitment to the pursuit of truth, a commitment that has left an indelible mark on the scientific world. Max Planck's contribution to the field of physics is foundational in shaping the course of modern science. The impact of his work goes beyond his own theories, as his revolutionary ideas laid the groundwork for the quantum mechanics that would emerge in the 20th century. His ability to solve long-standing scientific problems with elegant solutions introduced a new way of thinking about energy and the behavior of matter. Planck's quantum theory was not merely a mathematical correction, but a profound shift in how scientists understood the nature of the universe. His approach to physics was not about finding simple answers, but rather about re-evaluating the basic assumptions that underpinned classical physics. In the process, Planck became a pioneer in a field that was in its infancy and transformed the way scientists perceived the microscopic world. Max Planck's background was as much a factor in his scientific achievements as his intellect. Born into an academic family in 1858, Planck was encouraged to pursue knowledge from an early age. His father, a professor of law, and his grandfather, a theologian, instilled in him the values of rigorous thought and intellectual pursuit. While initially inclined toward engineering, Planck's academic path quickly shifted to physics, where he began his studies at the University of Munich and the University of Berlin. Under the guidance of renowned professors such as Hermann von Helmholtz, Planck absorbed the principles of thermodynamics, which would eventually guide his future work in understanding heat and energy. In the late 19th century, the field of thermodynamics had reached an impasse. Classical theories were unable to explain phenomena like black-body radiation, which had stumped scientists for years. Black-body radiation refers to the radiation emitted by an idealized object that absorbs all incident light and re-emits it in a characteristic way. Classical physics, which was dominated by the laws of thermodynamics and electromagnetism, predicted that as an object's temperature increased, it would emit more energy at higher frequencies, a prediction that led to the ultraviolet catastrophe. According to classical theory, objects would emit infinite energy at shorter wavelengths, something clearly not observed in reality. Scientists had no answer to this problem, and the need for a new theory was apparent. Planck's insight came not by adhering to the established norms but by daring to question the assumptions of classical physics. He recognized that the laws governing heat and energy could not be accurately described by classical physics at very small scales, particularly with regards to the emission of radiation by hot objects. Planck's brilliance lay in his realization that energy was not emitted continuously, as classical physics assumed, but in discrete packets or quanta. This was a revolutionary concept, for it suggested that energy could only be exchanged in specific amounts, rather than flowing smoothly and continuously. This idea was rooted in the mathematics of statistical mechanics and thermodynamics, but its consequences were far-reaching. To understand why Planck's theory was so radical, it's essential to recognize the central assumptions of classical physics at the time. According to classical theories, energy was considered a continuous variable, and the laws of thermodynamics were built around this assumption. Energy flows were thought to be smooth and predictable, with no underlying granularity. Planck's quantization of energy contradicted these fundamental ideas. Instead of continuous flows of energy, Planck suggested that energy could only be emitted in discrete chunks, proportional to the frequency of radiation. These quanta were not an ad hoc invention, but a necessary feature of his mathematical solution to the blackbody radiation problem. In 1900, after much contemplation and mathematical analysis, Planck arrived at his formula for blackbody radiation. His equation matched experimental data perfectly, solving the long-standing problem and dispelling the ultraviolet catastrophe. Planck's formula described the intensity of radiation emitted by a black body at different wavelengths, and it introduced the constant h, now known as Planck's constant, which quantified the discrete units of energy. Planck's equation was a monumental breakthrough, providing a way to understand the behavior of radiation that classical physics could not. However, Planck himself was initially hesitant to accept the full implications of his discovery. He saw his quantum hypothesis not as a new theory but as a mathematical trick, a temporary measure to resolve the problem of radiation. What Planck did not yet realize was that his solution had far-reaching consequences. Although he saw his quantum hypothesis as a provisional fix, the seed had been planted for a paradigm shift in physics. Planck's introduction of quantized energy levels was the first crack in the classical view of the universe, and his work laid the foundation for a new way of thinking about energy, matter, and the laws of physics. While Planck's own view of his work was limited, others soon took up his ideas and expanded upon them in ways he could not have anticipated. One of the first scientists to build upon Planck's ideas was Albert Einstein. In 1905, Einstein used Planck's quantization of energy to explain the photoelectric effect. The photoelectric effect demonstrated that when light of a certain frequency strikes a metal surface, it can cause the emission of electrons from that surface. Classical wave theory could not explain why only light above a certain frequency was able to cause the emission of electrons, but Einstein's interpretation, based on Planck's quantum theory, suggested that light itself was quantized in discrete particles called photons. This was a monumental breakthrough, as it showed that light had both particle-like and wave-like properties, a concept known as wave-particle duality. Einstein's work on the photoelectric effect won him the Nobel Prize in Physics in 1921 and helped cement the credibility of quantum theory. Einstein's work, along with that of other physicists such as Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, formed the foundation of quantum mechanics, a theory that would revolutionize the understanding of the microscopic world. Planck's ideas were critical in this development, even if he did not fully embrace the complete implications of his work. Quantum mechanics challenged the classical worldview, introducing concepts such as uncertainty, probability, and superposition, which contrasted sharply with the deterministic nature of classical physics. The impact of quantum mechanics on science and technology has been immeasurable, leading to innovations in fields ranging from computing to medicine. Despite the radical nature of his work, Max Planck remained a humble figure throughout his career. He was not driven by the desire for fame or recognition, but by a deep sense of intellectual curiosity and a commitment to understanding the fundamental laws of nature. His contributions to physics were not merely the result of individual brilliance, but also of perseverance and dedication to solving problems that others could not. Planck's approach to science was one of intellectual rigor, and his legacy has endured through the generations. As the world moved into the 20th century, Planck's work became increasingly recognized, not just by his contemporaries, but by future generations of scientists. His ideas provided the basis for much of the physics that would shape the 20th century, including the development of nuclear energy, quantum computing, and advanced materials. His work demonstrated the importance of thinking outside the box and challenging established ideas, a lesson that remains relevant in science and in life. Planck's contributions were not limited to his own theories, but also to the broader scientific methodology of questioning assumptions, testing ideas, and revising theories in the face of new evidence. The significance of Max Planck's work cannot be overstated. His quantum theory not only solved the blackbody radiation problem, but also launched a revolution in physics that fundamentally changed the way we understand the universe. Although Planck himself did not fully embrace the broader implications of his discoveries, his work sparked a series of developments that reshaped our understanding of energy, matter, and the nature of reality itself. Today, his name is synonymous with quantum theory, and his legacy endures as one of the greatest scientists in history. Max Planck's scientific journey not only reshaped the landscape of physics, but also laid the groundwork for what would become one of the most profound revolutions in human understanding. His work on blackbody radiation and his subsequent formulation of quantum theory proved to be the linchpin that initiated the quantum revolution, which would redefine how we understand the very fabric of reality itself. While Planck's initial hesitation to accept the full implications of his work reflected his cautious nature, it was clear that his insight into quantization would have far-reaching consequences. Planck's contribution to physics cannot be fully appreciated without understanding the cultural and intellectual context of the time. The late 19th century was a period of intense scientific development, with classical physics in its prime, establishing an understanding of the laws of motion, energy, and matter. However, despite the triumphs of classical mechanics, there were problems emerging in certain areas of physics that classical theory struggled to explain. Among these challenges, the most pressing issue was the problem of blackbody radiation. Blackbody radiation is a phenomenon where a perfect absorber and emitter of radiation, a black body emits radiation in a spectrum that depends only on its temperature. Classical theories, particularly those based on the laws of thermodynamics and electromagnetism, could not explain the observed behavior of radiation at high frequencies. Classical models predicted that the energy emitted would increase infinitely at shorter wavelengths, leading to the so-called ultraviolet catastrophe. This gap in understanding stood as a significant challenge to the scientific community. At the time, scientists had been unable to reconcile the experimental data with the predictions made by the classical theories. The existing laws, such as those put forth by Rayleigh and Jeans, were clearly insufficient in explaining the radiation emitted by black bodies, particularly at high frequencies. Their predictions failed to match the actual behavior of the radiation observed in experiments, and this discrepancy left physicists searching for a new solution. It was against this backdrop that Planck began to tackle the problem. Working with the empirical data collected by his predecessors, Planck set out to find a solution that would not only explain the behavior of blackbody radiation, but also provide a deeper understanding of the nature of energy itself. Planck's breakthrough came when he proposed that energy could not be emitted continuously, as classical physics had assumed, but rather in discrete units or quanta. This idea was a direct challenge to the classical worldview, which held that energy was a continuous variable. Planck's hypothesis suggested that energy was quantized and could only be emitted in specific amounts that were proportional to the frequency of the radiation. This new idea, which Planck introduced in 1900, was a radical departure from classical theories and was the beginning of the quantum revolution. To explain the behavior of blackbody radiation, Planck formulated an equation that perfectly fit the experimental data. The equation introduced a constant known today as Planck's constant, which describes the relationship between the energy of a photon and the frequency of the radiation. This was the first introduction of the concept of quantization in physics, and it offered a mathematical solution to the ultraviolet catastrophe that had stumped scientists for decades. The introduction of the concept of quantization was an enormous breakthrough. Planck's quantum hypothesis solved a pressing problem in physics, but the implications of his work were not immediately clear, even to him. He initially viewed his discovery as a mathematical convenience, a necessary tool to make sense of the radiation data, but he did not see it as a revolutionary change in the understanding of the physical world. Planck's work, though groundbreaking, was just the beginning of a much larger scientific shift. It took other physicists, most notably Albert Einstein, to take Planck's work and extend it into new realms of understanding. Einstein's work on the photoelectric effect in 1905 used Planck's concept of quantized energy to explain how light could eject electrons from a metal surface, a phenomenon that classical wave theory could not account for. Einstein's explanation of the photoelectric effect solidified the concept of quanta and earned him the Nobel Prize in Physics in 1921. It was also through the work of Niels Bohr, Werner Heisenberg, and Erwin Schrödinger that Planck's ideas grew into a fully developed theory of quantum mechanics. Bohr's model of the atom, for instance, introduced the idea that electrons could occupy discrete energy levels, an idea that was directly inspired by Planck's concept of quantization. Schrödinger's wave mechanics and Heisenberg's uncertainty principle further expanded upon Planck's initial work, leading to the development of quantum theory as we understand it today. The quantum revolution introduced a completely new way of thinking about the physical world, where particles could behave as both waves and particles, and where uncertainty and probability governed the behavior of subatomic particles. This was a far cry from the deterministic world of classical mechanics, where the behavior of objects could be predicted with absolute certainty. The shift from classical physics to quantum mechanics was one of the most profound revolutions in the history of science. It not only changed the way we understood the nature of matter and energy, but also gave rise to a host of new technologies that have transformed the world. Quantum mechanics is the foundation of modern electronics, including semiconductors and computer technology. It has led to the development of lasers, MRI machines, and other medical technologies, and it continues to drive advances in fields such as quantum computing and quantum cryptography. Max Planck's role in this transformation cannot be overstated. His work on black-body radiation was the spark that ignited the quantum revolution. However, it is important to recognize that Planck's contributions were not limited to quantum theory alone. His research in thermodynamics, his work on the second law of thermodynamics, and his insights into the nature of entropy were equally important in shaping the course of modern physics. Planck's ability to unify thermodynamics with statistical mechanics was another key contribution that helped form the basis for much of modern physics. His approach to science was always rooted in a deep respect for empirical data and a commitment to finding solutions to real-world problems, rather than simply building abstract theories. Throughout his career, Planck remained humble, not seeking fame or recognition, but focused solely on his work. Even in his later years, as he became more recognized for his contributions, Planck was known for his modesty and quiet dedication to science. His personal life, however, was marked by tragedy. During the Second World War, Planck lost his two sons, one of whom was executed by the Nazis, and the other was killed during the war. Despite these personal hardships, Planck continued to work and contribute to science until his death in 1947. His resilience in the face of such personal loss reflects the dedication and perseverance that characterized his approach to both life and science. Max Planck's scientific journey is a testament to the power of curiosity, persistence, and intellectual courage. His willingness to challenge the assumptions of his time and seek new solutions to long-standing problems has left an indelible mark on the history of science. Through his work, Planck not only solved a critical problem in physics, but also set the stage for one of the most profound revolutions in scientific thought. Today, his name is synonymous with quantum theory, and his legacy continues to shape the world of science and technology. The quantum revolution that Planck initiated has had a lasting impact on our understanding of the universe, and his ideas continue to inspire scientists and researchers across the globe. His work has truly stood the test of time, and his contributions remain foundational to the scientific enterprise. Max Planck's impact on the development of modern physics stands as one of the most monumental in scientific history. As the pioneer of quantum theory, Planck illuminated the path for future scientists, and his contributions reverberate through the fields of physics, chemistry, and even technology. His name is synonymous with the quantum revolution, which fundamentally changed how we understand the universe. His work not only solved a major problem in classical physics, but also laid the foundation for some of the most profound discoveries of the 20th century. This section delves deeper into Planck's contributions, examining how his insights catalyzed the scientific advancements that shaped the modern world. Born in 1858 inches, Kiel, Germany, Max Planck's early life was marked by academic excellence. His father was a law professor, and his family was steeped in intellectual tradition. Planck's early exposure to academia undoubtedly played a significant role in his later success in the sciences. Planck's formal education began at the University of Munich, where he studied engineering before shifting to physics. He later continued his studies at the University of Berlin, where he was mentored by prominent physicists, including Hermann von Helmholtz, who had a significant influence on him. Planck's academic career began with a focus on thermodynamics, a field that was pivotal to his later work on energy and radiation. However, it was the black-body radiation problem that would propel him into the spotlight of scientific history. In the late 19th century, the problem of black-body radiation had become one of the central puzzles of physics. Blackbody radiation refers to the radiation emitted by a perfect black body, an object that absorbs all incident radiation. Classical physics, which had dominated the scientific landscape, was unable to explain the behavior of this radiation at high temperatures. The existing theories predicted that energy emitted by a black body would increase infinitely as the wavelength decreased, leading to what was known as the ultraviolet catastrophe. This paradox posed a significant challenge to classical thermodynamics, which had successfully explained many other physical phenomena. The scientific community was left at an impasse, unable to reconcile the observed behavior of blackbody radiation with the predictions of classical physics. It was in this environment of uncertainty that Planck entered the scene. His approach to the blackbody radiation problem was not to simply accept the classical assumptions, but to challenge them. Instead of assuming that energy was emitted continuously, as classical theory had posited, Planck hypothesized that energy was emitted in discrete packets, or quanta. This was a radical departure from the classical understanding, which held that energy was a continuous flow. Planck's theory suggested that energy could only be exchanged in specific, quantized units, proportional to the frequency of the radiation. This bold hypothesis led to the formulation of Planck's law, a mathematical equation that accurately described the radiation emitted by a black body. The equation introduced Planck's constant, a fundamental constant in physics, which quantifies the relationship between energy and frequency. Planck's theory immediately solved the blackbody radiation problem. His equation accurately described the radiation at all wavelengths, and it eliminated the ultraviolet catastrophe that had plagued classical physics. The success of Planck's equation marked a significant breakthrough in the field of physics. However, Planck himself did not initially grasp the full implications of his discovery. He saw his quantum hypothesis as a mere mathematical convenience, a tool to resolve a specific problem, rather than a revolutionary concept that would transform the foundations of physics. Planck's reluctance to fully embrace the quantum nature of energy is reflective of the cautious mindset that characterized much of his career. Despite Planck's initial reservations, his work laid the foundation for the quantum revolution. His introduction of quantized energy levels was the first step toward the development of quantum mechanics. However, it was other physicists who would take Planck's work and expand upon it, creating the framework of quantum theory. Albert Einstein, in 1905, used Planck's concept of quantized energy to explain the photoelectric effect. Einstein's work demonstrated that light could not only be understood as a wave, as classical theory had suggested, but also as a particle. This dual nature of light, known as wave-particle duality, would become one of the cornerstones of quantum theory. Einstein's work on the photoelectric effect earned him the Nobel Prize in Physics in 1921, and his contributions, alongside those of Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, helped form the basis for quantum mechanics. The development of quantum mechanics was a significant shift from classical physics. Classical physics had been based on deterministic principles, where the behavior of objects could be predicted with certainty. However, quantum mechanics introduced a new way of thinking, where probability and uncertainty governed the behavior of particles. Planck's work on energy quantization was the spark that ignited this revolution. The subsequent development of quantum theory led to the creation of technologies that have transformed the world, including computers, semiconductors, and lasers. Quantum mechanics has also had profound implications in fields like chemistry, material science, and even medicine. With the advent of technologies like MRI machines and quantum cryptography, one of the critical elements of Planck's theory was the introduction of Planck's constant, h. This constant is a fundamental quantity in quantum mechanics, and it is used to calculate the energy of a photon, the smallest unit of light, based on its frequency. Planck's constant represents the quantization of energy and is a key part of the equation that describes the behavior of matter and energy at microscopic scales. The constant itself is an incredibly small number, approximately 6.626 x 10, negative 34 joule-seconds, but it has vast implications for understanding the nature of energy and matter. Planck's constant is one of the most important constants in physics and remains a crucial part of the mathematical framework that governs the microscopic world. Despite the revolutionary nature of his work, Planck remained a humble and cautious figure throughout his career. His contributions were not driven by a desire for fame or recognition, but by a deep passion for understanding the fundamental laws of nature. He worked diligently, often in isolation, and his contributions were not widely recognized during his lifetime. It was only in the years after his death in 1947 that the true magnitude of his work became fully appreciated. Max Planck's discoveries were not simply the result of genius, but also of perseverance, intellectual curiosity, and an unwavering commitment to scientific integrity. Throughout his life, Planck also played a significant role in shaping the future of physics through his mentorship and advocacy for scientific collaboration. He was instrumental in the establishment of the Kaiser Wilhelm Institute for Physics, which became one of the world's leading research institutions. Many of the great physicists of the 20th century, including Werner Heisenberg and Niels Bohr, worked under Planck's guidance. He was also a strong advocate for international scientific cooperation and helped foster the exchange of ideas between physicists from different countries. Planck's influence extended beyond his own work, and his commitment to scientific progress helped shape the direction of physics for generations to come. Max Planck's legacy is not just in the theories he developed or the mathematical equations he formulated, but also in the way his work has shaped our understanding of the universe. His pioneering ideas in quantum mechanics have opened up new fields of study and inspired countless scientists to continue exploring the mysteries of the microscopic world. Planck's contributions to science were not just about solving specific problems, but about reshaping the very way we think about the physical world. His work challenged established ideas and sparked a scientific revolution that continues to shape our understanding of the universe. Today, Max Planck's influence is evident in the way modern physics has evolved over the past century. His work was the starting point for a series of discoveries that have fundamentally altered the course of scientific history. Quantum mechanics, a field that Planck helped to create, is now one of the most successful and widely used theories in physics. It has revolutionized not only the way we understand the behavior of matter and energy at the smallest scales, but also the technologies that have changed the world. The quantum revolution that Planck initiated has had a profound impact on nearly every aspect of modern life, from the computers we use to the medical devices that save lives. Planck's work has made an indelible mark on the history of science, and his legacy continues to inspire scientists around the world to push the boundaries of human knowledge. Max Planck's contributions to physics not only revolutionized the field in his time, but also laid the foundation for much of the modern scientific world that followed. His insights, particularly the introduction of quantized energy levels, formed the bedrock upon which the entire quantum theory was built. His quantum hypothesis, proposed in the early 1900s, was not simply a solution to the black body radiation problem. It catalyzed the birth of quantum mechanics, a theory that would forever change the way we understand the universe. While Planck's initial discoveries were rooted in solving specific scientific issues, their profound implications slowly unfolded, reshaping physics and leading to breakthroughs that have shaped the modern world. When Planck first proposed his idea of energy quantization, the scientific community had yet to experience the disruptive shift from classical to quantum physics. At the time, classical mechanics and thermodynamics were sufficient to explain most of the natural world, but certain phenomena, most notably black body radiation remained inexplicable. The classical theories predicted that a black body would emit infinite radiation at high frequencies, which clearly contradicted experimental observations. This issue, known as the ultraviolet catastrophe, left a hole in classical physics, one that Planck was determined to address. His approach to the black body radiation problem was marked by mathematical ingenuity and theoretical boldness. Planck realized that the laws of classical thermodynamics, which governed energy and heat, could not explain the emission of radiation from heated objects. Instead of assuming that energy could be continuously emitted, Planck hypothesized that energy could only be emitted or absorbed in discrete packets, which he called quanta. This suggestion was groundbreaking because it fundamentally challenged the prevailing view that energy was a continuous variable. To solve the blackbody radiation puzzle, Planck introduced the concept of Planck's constant, a key part of his formula that governed the emission and absorption of radiation. This formula matched experimental data perfectly, resolving the blackbody radiation problem and eliminating the ultraviolet catastrophe. Yet, while Planck's solution to the radiation problem was a stunning success, he initially saw it as a mere mathematical tool, not a paradigm-shifting idea. He was hesitant to accept the full implications of his discovery, dismissing it as an interim fix. At the time, Planck did not fully grasp the enormity of what he had uncovered. He continued to believe that quantum mechanics was just a temporary solution to a specific problem, not a new theory that would reshape the fundamental understanding of the universe. He even went so far as to say that the concept of quanta might not be a true reflection of nature, but merely a useful approximation. Despite Planck's reservations, the scientific community quickly began to recognize the broader significance of his work. Albert Einstein was one of the first to extend Planck's ideas. In 1905, Einstein used Planck's theory of quantization to explain the photoelectric effect, a phenomenon that classical physics could not account for. The photoelectric effect showed that when light strikes a metal surface, it can cause the emission of electrons. Classical wave theory had predicted that the energy of the emitted electrons would depend on the intensity of the light, but experiments showed that the energy depended on the frequency of the light instead. Einstein proposed that light itself was quantized, and that it was composed of discrete packets of energy called photons. This insight led to the idea of wave-particle duality, a cornerstone of quantum mechanics. Einstein's explanation of the photoelectric effect earned him the Nobel Prize in Physics in 1921, and his work confirmed the validity of Planck's hypothesis. The implications of Planck's ideas grew even further as physicists like Niels Bohr, Werner Heisenberg, and Erwin Schrödinger developed quantum mechanics. Bohr's model of the atom, proposed in 1913, was directly influenced by Planck's work. Bohr suggested that electrons in an atom could only occupy specific, quantized energy levels, and that they could move between these levels by emitting or absorbing quanta of energy. This was an extension of Planck's concept of energy quantization, and it helped explain the discrete spectral lines observed in atomic spectra. Bohr's model of the atom was a significant step forward in understanding atomic structure and marked one of the first successful applications of quantum theory to the behavior of matter. By the 1922, quantum mechanics had emerged as a complete theory, with new developments emerging in every corner of physics. Werner Heisenberg introduced his uncertainty principle, which stated that it was impossible to simultaneously know both the position and momentum of a particle with absolute precision. Schrödinger developed wave mechanics, a mathematical approach that treated particles as waves, further expanding the concept of wave-particle duality. The uncertainty principle and wave mechanics revealed a new, probabilistic understanding of the microscopic world, in stark contrast to the deterministic laws of classical mechanics. Quantum mechanics showed that the behavior of particles at the smallest scales was governed by probabilities, not certainties, a concept that was difficult for many to accept. Despite the fact that Planck did not fully embrace the broader implications of quantum theory, his initial work was the catalyst that set the quantum revolution in motion. Quantum mechanics not only solved the long-standing problems of black-body radiation and atomic structure, but it also introduced a completely new framework for understanding the behavior of matter and energy. The principles of quantum mechanics have since become the foundation for much of modern physics and have had far-reaching consequences across multiple fields, from chemistry to technology. In addition to his theoretical contributions, Planck's work has had profound practical implications. The development of quantum mechanics has led to the creation of technologies that have transformed the world. The advent of semiconductors and the rise of modern electronics owe much to quantum theory. Computers, smartphones, and other electronic devices all rely on the principles of quantum mechanics to function. In medicine, quantum mechanics has enabled the development of technologies like MRI, magnetic resonance imaging, which relies on quantum properties of atomic nuclei to create detailed images of the inside of the body. Lasers, another product of quantum theory, have applications in everything from communication to medicine to entertainment. Max Planck's contributions to the development of quantum theory are nothing short of extraordinary. He not only solved a major problem in classical physics, but also paved the way for an entire field of study that has revolutionized our understanding of the universe. His work was a turning point in the history of science, marking the beginning of a new era in physics. Despite his own reluctance to fully embrace the implications of his discoveries, Planck's quantum hypothesis has become one of the cornerstones of modern physics. His legacy is felt not just in the theoretical advancements he helped bring about, but also in the practical technologies that have shaped our modern world. Max Planck's work is a testament to the power of intellectual curiosity, the courage to challenge established ideas, and the lasting impact that one person's insights can have on the course of human progress. Max Planck's work revolutionized the understanding of energy and matter, forever altering the course of physics. His introduction of quantum theory, sparked by his resolution of the black-body radiation problem, laid the foundation for one of the most significant scientific revolutions of the 20th century. Although Planck initially saw his breakthrough as a temporary solution, it ultimately led to the development of quantum mechanics, a theory that has since become a cornerstone of modern physics. The profound impact of his work not only transformed the scientific community, but also paved the way for technological innovations that shaped the modern world. Planck's journey into the realm of quantum mechanics began with his desire to solve a problem that had stumped physicists for decades: black-body radiation. Classical physics, dominated by Newtonian mechanics and the laws of thermodynamics, was unable to explain the radiation emitted by a perfect black body, a hypothetical object that absorbs all incoming radiation and re-emits it. Classical models predicted that, as the wavelength of radiation decreased, the intensity would increase without bound, leading to what was known as the ultraviolet catastrophe. This contradiction between theory and experimental data represented a significant failure of classical physics and created a void that required a new approach. Planck's solution to the black-body radiation problem came in 1900 when he proposed that energy was not emitted continuously, as classical physics had assumed, but rather in discrete packets, or quanta. This was a revolutionary idea because it challenged the very foundation of classical physics, which held that energy was a continuous variable. Planck introduced a mathematical formula that accurately described the emission of radiation by black bodies, which fit experimental data perfectly. Central to his formula was a constant, now known as Planck's constant, which related the energy of a photon to the frequency of the radiation. While Planck himself was initially reluctant to embrace the idea of quantized energy as a fundamental principle, his work solved the black-body radiation problem and laid the groundwork for the quantum theory that would follow. Despite Planck's groundbreaking solution, it was the work of other physicists, such as Albert Einstein, that fully realized the implications of his ideas. Einstein's explanation of the photoelectric effect in 1905 used Planck's quantum hypothesis to explain how light could eject electrons from a metal surface. This was the first major step in the development of quantum mechanics, as it demonstrated that light exhibited both wave-like and particle-like properties. The concept of wave-particle duality, which would become central to quantum theory, was born from Planck's early work. Einstein's work, building on Planck's insights, confirmed that light, like all electromagnetic radiation, could not be understood solely as a wave but as discrete packets of energy called photons. As the 20th century progressed, Planck's quantum hypothesis formed the bedrock upon which quantum mechanics was built. Niels Bohr's development of the Bohr model of the atom in 1913 incorporated Planck's ideas of quantization. Bohr proposed that electrons in an atom occupied specific energy levels, and that they could absorb or emit energy only when transitioning between these levels, thus quantizing the atom's energy states. Bohr's model, which successfully explained the spectral lines of hydrogen, represented a major advancement in atomic theory and was directly influenced by Planck's quantization of energy. This was the first application of quantum ideas to atomic structure, and it played a pivotal role in the establishment of quantum mechanics as a full-fledged theory. The development of quantum mechanics, further advanced by Werner Heisenberg's uncertainty principle and Erwin Schrödinger's wave mechanics, represented a fundamental shift in how scientists understood the behavior of matter at microscopic scales. Quantum mechanics showed that, at the subatomic level, particles did not follow the deterministic laws of classical mechanics. Instead, their behavior was governed by probabilities, with the uncertainty principle stating that certain pairs of properties, such as position and momentum, could not be simultaneously known with absolute precision. Schrödinger's wave equation described particles as wave functions, representing the probability distribution of their positions and momenta. These developments demonstrated the duality of particles and waves and the inherent uncertainty in measuring certain physical quantities, challenging the classical view of a predictable and deterministic universe. Planck's influence extended far beyond theoretical advancements. His work on the quantization of energy and his introduction of Planck's constant helped lead to the development of technologies that have revolutionized society. Quantum mechanics has been the foundation for innovations in electronics, computing, and communications. The advent of semiconductors and the subsequent creation of modern computers, smartphones, and other electronic devices relied heavily on quantum principles, particularly the understanding of energy levels in materials. Lasers, another product of quantum mechanics, have applications in fields ranging from telecommunications to medical imaging. The development of quantum technologies continues to evolve, with current research focusing on quantum computing, quantum cryptography, and other cutting-edge applications that promise to further transform the technological landscape. In addition to his contributions to physics, Planck played a significant role in the scientific community as a mentor and a leader. He was instrumental in establishing the Kaiser Wilhelm Institute for Physics in Berlin, which became a center for groundbreaking research in the early 20th century. Many of the leading physicists of the time, including Werner Heisenberg and Niels Bohr, worked at the institute, and Planck's guidance helped shape the next generation of quantum physicists. Planck was also a staunch advocate for scientific collaboration and international exchange, particularly during a time when Europe was experiencing political and social upheaval. His leadership and vision helped foster an environment of scientific inquiry that transcended national borders and laid the groundwork for many of the developments in quantum theory. Despite his profound contributions to science, Max Planck remained a humble and introspective figure. He did not seek fame or recognition, but was driven by a deep commitment to understanding the fundamental laws of nature. Even after his major breakthrough, Planck remained cautious about the implications of his discoveries. His reluctance to fully accept the full scope of quantum mechanics is a testament to his scientific integrity and his focus on empirical evidence rather than speculative ideas. His contributions were not born out of a desire to create a new theory, but rather from his determination to solve a specific problem. This humility and dedication to scientific progress make Planck one of the most revered figures in the history of physics. Max Planck's legacy is far-reaching, not only because of the groundbreaking work he did in theoretical physics, but also because of the practical implications of his discoveries. The development of quantum mechanics changed the course of science and technology, impacting everything from medicine to information technology. Planck's work continues to inspire scientists to challenge established ideas, think outside the box, and seek solutions to problems that may seem insurmountable. His contributions, particularly the introduction of quantized energy, provided the spark for one of the most transformative revolutions in human knowledge. Planck's place in the history of science is secure, and his legacy endures in the modern technologies that continue to shape our world. Max Planck's contributions to the field of physics mark a turning point in scientific history. His pioneering work on quantum theory, particularly his solution to the black-body radiation problem, ushered in a new era of understanding that fundamentally altered how scientists perceive the universe. While Planck is widely recognized as the father of quantum theory, his work was not an isolated event, but rather the beginning of a revolutionary shift in scientific thinking that would continue to unfold throughout the 20th century. His insights into energy quantization challenged the classical view of physics and provided the foundation upon which quantum mechanics would be built. Planck's most significant contribution came in 1900 when he addressed a long-standing issue in classical thermodynamics known as the black-body radiation problem. Classical physics, which had served as the foundation for scientific understanding for centuries, was unable to explain the observed radiation emitted by a perfect black body, an object that absorbs all radiation and re-emits it. Classical models predicted that energy emitted by a black body would increase infinitely as the wavelength decreased, leading to the so-called ultraviolet catastrophe. This failure of classical theory to match experimental data created a gap in scientific understanding, one that Planck was determined to address. In his pursuit of a solution, Planck introduced a groundbreaking hypothesis. Energy is not emitted or absorbed continuously, but in discrete units, or quanta. This concept of quantization was a dramatic departure from classical physics, which had assumed that energy flowed continuously. Planck proposed that the energy of a system could only take on discrete values, and these values were proportional to the frequency of the radiation emitted. This insight, which Planck derived through a combination of theoretical reasoning and mathematical manipulation, led to the formulation of what is now known as Planck's law. The equation that Planck developed successfully described the emission of radiation from a black body and resolved the ultraviolet catastrophe, marking a monumental achievement in physics. However, Planck himself did not immediately recognize the full implications of his work. At the time, he viewed his hypothesis as a mathematical device, a temporary solution to the problem of black-body radiation. Rather than a revolutionary new way of thinking about energy, Planck's reluctance to fully embrace the quantum nature of energy reflected the prevailing mindset of the time. Classical physics had dominated scientific thought for centuries, and the idea that energy could be quantized was a difficult concept to accept. Planck's hypothesis was an essential first step in the development of quantum theory, but it would take the work of other physicists to build on his ideas and fully realize the implications of his discovery. The true significance of Planck's work became apparent in the years that followed, particularly through the work of Albert Einstein. In 1905, Einstein used Planck's concept of energy quantization to explain the photoelectric effect, a phenomenon that had previously eluded explanation. Einstein proposed that light itself was quantized, existing in discrete packets of energy known as photons. This was a critical step in the development of quantum theory, as it introduced the concept of wave-particle duality, a central feature of quantum mechanics. Einstein's explanation of the photoelectric effect helped confirm Planck's hypothesis and earned him the Nobel Prize in Physics in 1921, further solidifying the importance of Planck's work in the scientific community. Planck's ideas also laid the groundwork for the development of atomic theory. Niels Bohr, in 1913, applied Planck's concept of quantization to the structure of the atom, developing the Bohr model of the atom. According to Bohr's model, electrons in an atom could only occupy specific, quantized energy levels, and they could move between these levels by absorbing or emitting quanta of energy. This model successfully explained the spectral lines of hydrogen and was the first major application of quantum theory to atomic structure. Bohr's work, which was directly influenced by Planck's earlier research, was a key step in the development of quantum mechanics. As quantum theory progressed, it became clear that Planck's contributions were foundational to the entire field. Quantum mechanics, developed by Werner Heisenberg, Erwin Schrödinger, and others, replaced classical mechanics as the dominant theory for understanding the behavior of matter at the atomic and subatomic levels. Quantum mechanics introduced a probabilistic view of the microscopic world, where particles could exist in multiple states simultaneously, and their behavior could only be predicted in terms of probabilities. This represented a profound departure from the deterministic world of classical physics, where the future behavior of a system could be precisely predicted. In addition to his theoretical contributions, Planck's work has had far-reaching practical implications. The development of quantum mechanics has led to innovations in a wide range of fields, from electronics to medicine. The principles of quantum mechanics underpin the technology that drives modern computers, smartphones, and other electronic devices. The development of semiconductors and the invention of the transistor, which rely on quantum principles, have been pivotal in the advancement of technology. Quantum mechanics has also led to the development of technologies such as lasers, which have applications in telecommunications, medical treatments, and entertainment. Despite the monumental impact of his work, Planck was not driven by the pursuit of fame or recognition. He was a deeply committed scientist, focused on solving problems and advancing human knowledge. Throughout his career, Planck remained humble, often attributing his success to the collaborative efforts of the scientific community rather than his own individual brilliance. He was also dedicated to the advancement of science in a broader sense, working to promote scientific collaboration and international exchange, especially during a time when Europe was embroiled in political and social upheaval. Planck's work has left an indelible mark on the history of science. His contributions to quantum theory not only solved a critical problem in physics, but also laid the foundation for an entire field of study that has transformed our understanding of the universe. His theories have had a profound influence on the development of modern technology and have opened up new areas of research in fields ranging from particle physics to quantum computing. Max Planck's work continues to inspire generations of scientists to push the boundaries of knowledge and to challenge the assumptions of the past. Through his groundbreaking research, Planck illuminated the path to a new understanding of the universe and his legacy continues to shape the future of science. Max Planck's legacy in the history of physics is irreplaceable, marking a profound shift in scientific thought that bridged the gap between classical physics and quantum mechanics. His work on black-body radiation and the introduction of energy quantization not only solved a critical problem in thermodynamics, but also laid the foundation for the quantum revolution. While Planck's contributions were initially met with reluctance and skepticism from his peers, his ideas ultimately sparked a new way of understanding the physical world that would influence generations of physicists. In the late 19th century, classical physics was facing an impasse. Although it had successfully explained a wide range of phenomena, certain problems remained unresolved, the most notable of which was black-body radiation. A black body is a theoretical object that absorbs all radiation falling on it and emits radiation based on its temperature. Classical theories, including those developed by Rayleigh and Jeans, predicted that the intensity of radiation would increase infinitely at shorter wavelengths, particularly in the ultraviolet region. This prediction, known as the ultraviolet catastrophe, was clearly contradicted by experimental observations. The failure of classical theory to explain this behavior left scientists in search of a new solution. Max Planck approached this problem by introducing a revolutionary idea. Energy is not emitted or absorbed in a continuous manner, but in discrete units, or quanta. This was a radical departure from the classical view that energy could flow continuously. Planck proposed that the energy of a system was proportional to the frequency of radiation, and that energy could only be emitted in specific, quantized amounts. This idea of quantization was groundbreaking and laid the groundwork for what would become quantum theory. To describe the radiation emitted by a black body, Planck derived a mathematical formula that matched the experimental data perfectly. His formula, which introduced Planck's constant, resolved the ultraviolet catastrophe and provided a successful model for black-body radiation. However, Planck himself did not fully grasp the deeper implications of his discovery at the time. He saw his quantum hypothesis as a temporary mathematical solution, not as a fundamental shift in our understanding of the universe. Despite Planck's initial reluctance to embrace the broader significance of his work, his ideas provided the foundation for the quantum revolution that would follow. The next major step came with Albert Einstein, who, in 1905, used Planck's quantum hypothesis to explain the photoelectric effect. The photoelectric effect involves the emission of electrons from a metal surface when exposed to light. Classical wave theory could not explain why only light above a certain frequency could cause this effect. Einstein proposed that light consisted of discrete packets of energy, or photons, and that the energy of each photon was proportional to the frequency of the light. This idea of wave-particle duality, where light could behave both as a wave and as a particle, was a direct extension of Planck's quantum hypothesis and helped solidify the validity of quantum theory. Einstein's work on the photoelectric effect earned him the Nobel Prize in Physics in 1921, and it was instrumental in the acceptance of quantum theory by the scientific community. In the years that followed, Planck's work served as the foundation for the development of quantum mechanics. Niels Bohr, in 1913, applied Planck's quantization of energy to the structure of the atom. Bohr's model, which proposed that electrons in an atom could only occupy specific energy levels, was a direct extension of Planck's concept of quantization. This model successfully explained the discrete spectral lines observed in hydrogen atoms and marked the first successful application of quantum theory to atomic structure. Bohr's work was pivotal in the development of quantum mechanics and was directly influenced by Planck's early contributions. The development of quantum mechanics continued with the work of Werner Heisenberg, Erwin Schrödinger, and others. Heisenberg's uncertainty principle, introduced in 1927, posited that it was impossible to simultaneously know both the position and momentum of a particle with absolute precision. This introduced a probabilistic nature to the behavior of particles, a stark contrast to the deterministic world of classical physics. Schrödinger's wave mechanics, which treated particles as waves, provided a mathematical framework for understanding the behavior of particles at the quantum level. Together, these developments formed the core of quantum mechanics and represented a complete departure from the deterministic views of classical physics. Planck's ideas also had a profound impact on technology. The principles of quantum mechanics underpin modern electronics, including semiconductors, which are the foundation of modern computers, smartphones, and other electronic devices. The development of quantum theory also led to the creation of lasers, which have applications in a wide range of fields, including telecommunications, medicine, and entertainment. The field of quantum computing, which seeks to harness the principles of quantum mechanics to perform computations far beyond the capabilities of classical computers, is another direct consequence of Planck's work. Throughout his career, Planck remained a humble and reserved figure, focused on the pursuit of knowledge rather than fame or recognition. Despite the immense impact of his work, Planck did not seek to become a public figure. He was driven by a deep curiosity about the natural world and a desire to solve scientific problems. His contributions to physics were not the result of a desire for personal glory, but rather of his dedication to the advancement of human understanding. Planck's legacy is not just in the theories he developed, but also in the way his work inspired future generations of scientists to challenge established ideas and explore new frontiers in physics. Max Planck's work transformed the landscape of science and technology, and his contributions continue to influence the direction of modern research. Quantum theory, which began with his work on blackbody radiation, has had a profound impact on every aspect of our lives, from the technology we use daily to the way we understand the universe at its most fundamental level. Planck's ideas laid the foundation for a scientific revolution that has reshaped physics, chemistry, and engineering, and his legacy endures in the groundbreaking discoveries and technologies that continue to emerge from the field of quantum mechanics. Max Planck's contributions to the field of physics represent one of the most transformative periods in scientific history. His work in the early 20th century laid the foundation for quantum theory, revolutionizing our understanding of energy, matter, and the very nature of reality itself. Planck's introduction of the idea that energy is quantized, rather than continuous, marked a departure from the classical physics that had dominated for centuries and set the stage for the quantum revolution. His legacy, though initially underestimated, became one of the cornerstones of modern physics. At the time when Planck began his research, the scientific community was grappling with a significant problem that classical thermodynamics could not solve: blackbody radiation. A blackbody, defined as an object that absorbs all incident radiation and re-emits it, showed a behavior that classical theories couldn't explain. Classical physics, based on the laws of thermodynamics and electromagnetism, predicted that as the temperature of a blackbody increased, its radiation intensity would increase infinitely at shorter wavelengths, leading to a phenomenon known as the ultraviolet catastrophe. This was a critical failure of classical physics, as it contradicted experimental observations. Scientists were at a loss, and the need for a new approach was evident. In 1900, Planck stepped into this intellectual void with a solution that would change the course of physics. His breakthrough came when he proposed that energy is not emitted or absorbed continuously, as classical theory had suggested, but in discrete amounts, or quanta. This was a radical departure from the prevailing assumptions, as it introduced the idea that energy is quantized. To describe the radiation emitted by a blackbody, Planck formulated a mathematical expression that described how energy levels would behave in relation to frequency. This formula not only solved the blackbody radiation problem, but also introduced Planck's constant, a new fundamental constant in physics that became key to understanding energy at the quantum level. The constant, denoted as h, was the proportionality factor between the frequency of radiation and the energy of a photon, and it would become central to the field of quantum mechanics. While Planck's discovery solved a specific problem, it was not immediately recognized for its broader implications. Planck himself saw the idea of quantization as a mathematical convenience rather than a reflection of the true nature of reality. His work was seen as a necessary adjustment to existing theories, but he did not foresee that it would lead to a revolution in the way scientists would approach the study of the universe. Despite this, his concept of quantized energy laid the groundwork for future developments in quantum theory. It would take other physicists, particularly Albert Einstein, to fully recognize and expand upon the significance of Planck's work. In 1905, Einstein used Planck's quantization concept to explain the photoelectric effect, a phenomenon in which light shining on a metal surface causes the emission of electrons. The problem, as Einstein noted, was that classical wave theory could not explain why light below a certain frequency failed to release electrons regardless of its intensity. Einstein proposed that light consisted of particles, or photons, each carrying energy proportional to its frequency. This was a direct application of Planck's hypothesis and helped establish the wave-particle duality of light, a cornerstone of quantum theory. Einstein's explanation of the photoelectric effect not only confirmed Planck's ideas but also earned him the Nobel Prize in Physics in 1921, bringing broader attention to Planck's work in quantum theory. As quantum theory developed in the following decades, Planck's work continued to inspire the next generation of physicists. Niels Bohr, in 1913, applied the idea of quantized energy levels to atomic structure, proposing that electrons in atoms could occupy only specific energy levels and could transition between them by absorbing or emitting energy in discrete amounts. This was a direct extension of Planck's concept of energy quantization. Bohr's model successfully explained the spectral lines observed in hydrogen atoms, marking the first application of quantum theory to atomic structure. The development of quantum mechanics was further advanced by the work of Werner Heisenberg and Erwin Schrödinger. Heisenberg's uncertainty principle, introduced in 1927, stated that certain pairs of properties, such as position and momentum, cannot be simultaneously measured with arbitrary precision. This introduced an inherent uncertainty to the behavior of particles at the quantum level. Schrödinger, on the other hand, developed a wave equation that treated particles as waves, further extending the concept of wave-particle duality. These developments, which built upon Planck's early work, formed the framework of quantum mechanics, a theory that would replace classical mechanics in describing the behavior of matter on the atomic and subatomic levels. Quantum mechanics, which evolved from Planck's work, not only transformed physics but also led to significant technological advancements. The development of semiconductors based on quantum principles gave rise to the modern electronics industry. Transistors, which are the building blocks of modern computers and smartphones, rely on quantum mechanics to function. Similarly, quantum theory has played a key role in the development of lasers, which have applications ranging from telecommunications to medical treatments. The principles of quantum mechanics continue to underpin emerging technologies, such as quantum computing and quantum cryptography, which promise to revolutionize fields like information processing and data security. Max Planck's work in quantum theory also had a profound impact on the scientific community. Throughout his career, Planck maintained a deep commitment to intellectual integrity, and his role as a mentor and leader in the scientific community was equally important as his theoretical contributions. Planck, was instrumental in the establishment of the Kaiser Wilhelm Institute for Physics in Berlin, where many of the leading physicists of the 20th century, including Werner Heisenberg and Niels Bohr, worked. Planck's leadership helped foster an environment of collaboration and intellectual exchange that was crucial in the development of quantum theory. Max Planck's legacy is immeasurable, not only because of his theoretical contributions, but also because of the lasting impact his work has had on science and technology. His ideas laid the groundwork for the quantum revolution, and his work has influenced not just theoretical physics, but a wide range of technological advancements. The development of quantum mechanics continues to shape modern science and technology, and Planck's contributions remain at the heart of these innovations. Planck's quiet dedication to understanding the fundamental laws of nature and his perseverance in the face of uncertainty have made him one of the most important figures in the history of science. His work has left an indelible mark on the scientific world, and his legacy will continue to inspire generations of scientists for years to come.